Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
A great pleasure to have Vittorio Ferrari here with us today. Vittorio comes from the world-famous ETH in Zurich and is about to move to another world-famous place, the University of Edinburgh. In fact, he's right in between right now. Traveling with his kid and wife. It was a great pleasure to meet them today. I was hoping for your son to give a talk, but he doesn't speak yet. So Vittorio is asking me that if there are any questions, throughout the talk, please feel free to ask. Raise your hand and ask a question. I'm not sure whether you should use a microphone to ask a question. No, you don't need to because there is plenty of microphones. But that's it. Take it away.
Am I on?
Yeah.
Yes. Okay. Very good. So thanks for coming to this talk that was announced so shortly. So I'm very glad that we have a compact, distinguished audience. I think we have time for a lot of questions according to my own timing of this talk and the total time of the seminar. So I welcome you to interrupt for clarifications or even challenges, whatever. I'm used to that. So today is my first working day at the University of Edinburgh. And as you can see, I'm already on travel. That's the life of the researcher. But the talk today will be about research that has been carried out at ETH Zurich. So the topic is weakly supervised learning of visual models. What do we mean under these buzzwords? So in this talk, these buzzwords means this, not something else. They mean learn appearance models that are able to localize a visual class in novel test images, given as training data only images labeled by the presence or absence of that class. So let's say the class in question is motorbike. This would be a case of a weakly supervised learning scenario. You would have a bunch of images, not just two, you would have hundreds, where you know there is a motorbike in each image, but you don't know where. You do something, you cook it up with some algorithms, some of them we'll see today, and you get some appearance model that you can then run on a new test image. And in a new test image, you can localize novel instances of the motorbike class. The class can be something else. It could be cauliflowers, or we will see people playing tennis. That's always a fun application if you're in Switzerland. But what matters is this notion of not having localization annotation at training time and wanting an output in localization format at test time. So that's why we call it weakly supervised. So why do we want to do that? Because we like to reduce the manual effort that it takes to train a visual category. If you have less manual annotation, it sounds cool, scientific, but it also has some practical consequences. Hopefully by investing the same time to manually annotate data, you can annotate more classes, or you can annotate the same number of classes, but with many more training examples. Especially if the annotation is only image labels, you can go at an incredible speed today with image search engines such as Bing, or should I call Google Images, but let's say Bing then. You could really go really quick and collect tons of images of motorbikes and rapidly sift through them and remove those that don't have the motorbike, and then you're ready in this setting. Whereas marking outlines or bounding boxes typically much slower. The only problem with this beautiful story is that, at least today, state-of-the-art weakly supervised is not as good as fully supervised. What do we mean by as good? After you run your learning algorithm, you give a test data set, and the ability to localize object instances for a model that's trained with full supervision is typically higher than the ability of a weakly supervised model. So there are really too many works to cite them all. Here are a few of the maybe most popular ones of the recent years. In this talk, I am going to present certain works we did at my research group, which is called Calvin at ETH Zurich, and soon to migrate to Edinburgh. And we have been devoting quite a lot of effort in the last 2 years in trying to bridge this gap, in trying to make weakly supervised learning techniques that would produce models that perform less bad compared to fully supervised ones. We didn't close the gap yet, so we can already go to the end of the talk. That would be a miracle. But I think we got a lot farther than we were a few years ago. Among the many subforms in which the general problem appears, there is the problem of localizing object categories up to a bounding box. That's what I have shown as an example before. Another thing you can do instead is, I should be here, sorry. So if this is your training data, you're given images of motorbikes or of horses. One problem is to localize objects up to a bounding box. Another one is to localize objects up to a pixelwise segmentation, which is a harder problem. Another thing we would like to do is to go basically from here to here, is learning visual classes that are composite of a person in a particular posture and an object that interacts with the person, such as in tennis serving, or in drinking from a coffee mug, or shooting with a gun. And then a fourth problem we have looked at is, I would believe originated in this lab from man over there, is the problem of semantic segmentation, where you are given input in this form, where you have multiple object classes and background classes. The image is labeled by all the classes it contains, and what you want to try to do is to label every pixel with its semantic class. So we have done work in all these 4 areas, but today, in the interest of depth, I'm going to present 2 recent works only, on the human-object interaction side and on the multi-class semantic segmentation side. So all the works I've mentioned here on the slide and the 2 works today are all weakly supervised. So we never have location annotation for training. So off we go. I start immediately from a generic component that we tend to, secret sauce that we tend to splice on every paper we write, and I would like to advertise it. And it's called the objectness measure. So this we published it first in 2010 at CVPR. The idea is to make a function that can take a window as input and can output a probability for that window to contain an object of any category. And by object, we mean things in the psychology literature that have a well-defined closed boundary in space that you could grab. So examples of objects are sheep, and Antonio, and a chair, and a microphone. And these are in contrast to background categories, also called stuff in psychology literature, which are essentially backgrounds like grass, water, sky, rock, mountains, things which are there in an amorphous shape rather than in a concrete, grabbable form. And one might think this distinction is a bit fuzzy, but actually there exist properties that are specific to all objects as opposed to backgrounds, such as typically objects have these well-defined boundaries, as I said, but often they have a different appearance than their surroundings. Like this sheep, they are a bunch of white against a green background. And sometimes objects are unique within the image, such as here there is a single red car in the whole image. So this last property is often called saliency in the literature. So saliency is part of the story of objects, but not all of it. If you would have a pattern of 300 sheep, they would all be objects, although they are not salient. So the ideal behavior of an objectness measure, if we could build it, is to give a highest possible probability to windows that fit an object tightly, like the green windows here. Then it should give the lowest possible probability, around 0, to windows that are completely only on background stuff, like the red windows here. And ideally, you would get an intermediate probability shade in windows that cover a bit of an object, a bit of background, like blue here. So if you could have such a measure, why on earth would you use it? What is it useful for? And actually, this is an important point in weakly supervised learning. What you can use it for, you can use this probability output to bias your weakly supervised learner towards picking objects rather than stuff or background as an answer. So the issue is maybe exemplified by, imagine you have 100 images of sheep against grass. The key of all these algorithms is always to find recurring patterns of appearance. The object is typically something that looks similar across all the images. So why not a 10 by 10 window on the grass? Well, that's green and textury the same way in all the 100 images. That would be a perfectly valid answer for a weakly supervised learner if the only force you give to it is to find recurring patterns of appearance. But if now you ask it, find something recurring that is an object, then it's no longer be able to answer you a little patch of grass. It will have to answer something else. Maybe the answer is not the sheep. Maybe it's still wrong. But the space of possible answers became a lot smaller. And that typically helps the weakly supervised learner. So that's already basically the spirit of a lot of the works we do, is to inject this objectness measure inside algorithms to make them skew to objects. So how well does it work? First, I didn't tell you how it works. What is it? And this is not really the subject of the talk. There are a number of image features you can measure and many ways you can engineer them together in machine learning fashion to operate well. I recommend you to look at our CPR10 paper. In this work, I'm going to talk how to employ it within weakly supervised learning algorithms. But to encourage you to try it out, because we have source code online, I give you some feeling for how well does it work. So we ran our method on the PASCAL VOC 2007 test set. And basically, what you can plot is, if you ask the objectness measure to return you a certain number of windows on the x-axis, then you can measure how many of the ground truth objects in the 20 categories of Pascal are covered by at least one of these windows, so detection rate. And then you can see how much you need to sample before you cover most of the objects. And of course, this is a very difficult data set, so even getting to 70, 80% is already great. And what is funny is that if you are ready to pay 1,000 windows, which is not a lot, a typical sliding window algorithm would read 100,000 or 500,000, then you're already in the 91% detection rate. So basically found everything that's feasible on this data set.
So how tight is the window? What sort of tightness level? Because you can always say the whole image is
That's excellent. Right? Very good. So in this plot, this is the Pascal detection criteria, which is intersection of over union of the area 50%.
Mm-hmm.
This is reasonably tight. People often complain it's too tight, but actually it depends for what union to use it. It might not be tight enough. So this is the evaluation I have here. You could try to look at it otherwise.
This question, did you try to say, don't look at the image, try the optimal configuration of 1,000 windows? What score would you get? 0.
The location prior.
No, not even without location prior. What's the optimal cover of 1,000 windows so that you...
That's an excellent question. Okay, what is the optimal cover? That is, you don't take the image pixels. You look at the training data and you say...
You don't even look at any image. You don't look at the training data. You just say, give me 1,000 images so that you optimize the scores that you get best. You might already get at 0.5. Because if you go to a large number, you might actually, with the...
This is a good question, but how would you do it without training data? That depends on what is the distribution of locations of objects in images.
Then you can take that in as well, yeah.
Because if you ask me that question, I have an answer.
Okay, what's the answer?
So in our journal version of this work, which is available on our website, we tried to train a location prior, so a 4D distribution for this, the dimensionality of a window, over the training data. And actually, location priors do pretty well with many windows. So it's not here. You can see it in our journal. A location prior at 1,000 windows would already get into the 60%, which is far below where we are, but still very reasonable. Yeah. But what is the advantage is when you go down. At about 10 or 100 windows, maybe I show it here. At 100 windows, we are now at 70-something%. And at 10 windows, you're already almost at half. And with the location prior, you're nowhere. So it takes a while to take off. So depending on how much you want to pay, then indeed, after a while, you're not interested in this. If you're ready to pay 100,000 windows, then just go location priors. A very important second aspect is not only the ability to detect objects with few windows, which is interesting for computational efficiency, but what is most important is not in this plot. What is most important is that you get a number out, a probability, how likely it is to be an object. And that's what we will use in this talk as a bias for the weakly supervised learner. So to conclude, you can conclude this little advertising. You can download the code from our website. It has been used in a number of works beside our group. In our group as well, but also beside our group to actually do weakly supervised learning. But people have been creative. They have started to do other things like content-aware image resizing. That was quite surprised. People like to shrink images without losing the objects, rather lose the background. People have started to use it for this purpose. And also some object tracking video is going on. So now we get to the actual technical core of the talk, where I will describe these two recent works. In the first part, we are going to try to learn visual classes, which are defined as human-object interactions. So here is one example, cricket batting, like these three guys. The goal is to get a series of images which you all know contain a person that is in the cricket batting action. And we want to localize both the person and the object, the action object, which is unknown at the beginning. And we want especially to learn a spatial model of the human-object interaction. So after learning, the computer should be able to say, when somebody's cricket batting is doing it this way, is not doing it, say, this way or this way. Well, if it would do it this way, it probably wouldn't win many matches. But, it's doing it from below. And that's actually the output that we really aim for. And then once you have such a model, you can use it to classify test images to know if they actually have somebody cricket batting. If you would just have a person and a bat on the floor, you should not say that they are cricket batting. It's the interaction that matters. So here is some motivation for it. There is really maybe too much work on action recognition in vision. And most of it is on video, spatial temporal features. Some of them are on still images. But typically there is a single actor. An action is something like running or so. A few recent works, they try to do actions as human-object interactions. So tennis serving, cricket batting, cooking coffee or so. And basically all of those we know but ours require full supervision. And typically full supervision is very heavy. It's not just bounding boxes around objects and people, which is already heavy, but it's even silhouettes, complete pixel-wise segmentations of people, and sometimes even stickmen, like in the work of Ramanan. Here we try to do it only with image labels. And how are we going to do that? We need some other source of force, another source of supervisory signal that can help us. And what we are going to exploit is that the human-object spatial relation is rather constant across the images. So we don't know how the person is holding the cricket bat, but we know that he should be holding it in the same way in all the images. And of course, the action object appearance should also be recurring. So we published this in PAMI 2011, and the core of the learner is to automatically try to localize the action objects in the training images. How are we going to do this? Well, we start by automatically detecting humans. That's not too difficult in this kind of imagery because of, thanks to recent developments like Felsenzob and Ramanan. If you know there is a single person in the image, this works pretty well. Then we are going to use the detected person as a reference frame. And we're going to try to ask the question, localize the object on object, so that it recurs a similar position with respect to the human bounding box. This is our model. I'm going to go through the terms a little bit. The model is defined, it gives an energy to a configuration of windows. It's going to select one window in every training image, trying to maximize, actually to minimize this energy. If you would visualize this with a graphical model, it would look a little bit like a fully connected conditional random field. But maybe it's easiest to think of it just as an energy function. We are going to start by defining a set of candidate windows where the object could be. And for this case, we use 500 objectness windows. On these datasets, that's a 100% detection rate at PASCAL detection criterion above 0.9. So it's just perfect. You don't want more. So 500 candidate windows are very much enough. And then the question is find one windows per image minimizing this energy. And what are the energy terms? We're going to have some unary term. So one variable will be one image, not a pixel in an image. One variable is an image. And the state space of an image is which candidate windows do I pick. So far, so good? So the unary term in this case, it's a score that decides how good is a window. One only window in one image. We are going to use the objectness probability as that score. Then we have pairwise potentials. In this case, pairwise potentials, they're not like in traditional works, like what is the similarity between two pixels in an image. In this case, it's what is the similarity between two windows in two different images. So we have a window in an image, candidate, say this one, and another candidate in the other image. And now we can measure a pairwise potential between these two. And we are going to see this pairwise potential contains the human-object spatial relation similarity. We're going to go through the terms in more detail after this overview. And the second pairwise potential will be the similarity in the appearance of the object itself. So the energy function will like to select windows so that the appearance between the selected windows is more similar as possible. So let's start from this last term. This is this term here. So basically, if you have two candidate windows, here is a visualization of some candidate windows into training images. If you have two candidate windows, you can now measure the chi-squared similarity between the bag of word histogram or color histogram or hog, whatever you like to do. We do color histograms and spatial pyramid of surf, but it's not so important. You can measure the chi-square similarity and use it as a pairwise potential here. Then we get to the true interesting part of the model, I would say, the human-object spatial relation similarity. So this is basically a potential that involves four entities. There is a human detection in one image and a candidate window in that image. You can measure the spatial relation between these two. For example, the relative position or the relative area. Now you get one number. Now you can compare that number to the analog number computed in the other image. Because it's a pairwise potential, it connects two images. So let's say you look at the relative area. The racket is a bit bigger than this person, The same here. Then you can conclude these two candidate windows are preferred by the energy. Here are the actual spatial relation that we are going to measure in a visualization that should help you understand them. Relative scale works as follows. Here there will be 2 training images, and here is a 3rd training image. The human is fixed, remember, and the O window is a candidate window that could be an object. So it's one of the states of the random field. If you compare a pairwise potential, if you look at a pairwise potential between these 2 images, you get low energy in all the cases in this column, because the object is smaller than a human by a certain factor, and it's smaller here by the same factor. Therefore, the random field is happy, the energy is low. Whereas here, it will not be happy, it will give you a high energy, because the object became a lot bigger. And you can play the same game. Instead of relative scale, you can do relative distance, overlap, location, or angles, whatever other measure we use this for. So let's go back. So this becomes this term. This prefers selecting windows that have similar appearance. This prefers selecting windows which have a similar location with respect to the human. And this prefers windows with high objectness. Once you have the model set up, you can now run inference on it to select a single window per image so that's to minimize the energy. And for this, we use 3-dimensional message passing by Kolmogorov. Yes?
So I don't understand, do you learn it or do you handcraft that energy? I mean, is there some learning involved or not?
So the learning of the energy itself, the output of inference on this energy would be what we would call learning. But there is also a level of learning above that, which is what is the weighting between the terms. And that we also do on a higher level, but it's not part of this talk. Maybe we talk about it later. That would be, we do that with constraint generation.
But while you're in front of your big data set, while you run TRWS, you kind of learn the system of getting jointly out the best thing of
Yes. The output of TRWS is a configuration of windows, 1 per image.
Yeah.
And with that, we are going to use that to learn a spatial model. That's actually a learning act is the inference here. But there is a meta-learning level of knowing what are the weighting of. That's out of this talk, but it's in our journal as well. So actually, we connect every training image to everyone in this. It's a fully connected model with 500 states per node. Arbitrary pairwise potential, so to our understanding, you cannot do it exactly. Therefore, we run TRWS. But what is fun is that it gives you the dual gap. And you can actually measure how many times you got the global optimum. And although this looks like a difficult problem, in practice, we get the global optimum in about 95% of the instances of the problem. And the other times is about 1%, the dual gap, to the ratio of the 2 energies, about 1%. So it works very well.
So how many labels, so how many windows do you sample?
500 in every image. So
and is it the same for every image, or can
no, it changes. Every image has a different state space.
Okay.
And you sample them randomly?
Oh, how do we sample them? Yes, in this work, we have this objectness function running over, and then we sample from the objectness function. This means sometimes it gives you low probability windows, sometimes high probability ones. But you could do no maximum suppression instead, which is what we do recently, works a bit better. Then you only get the high state, high energy one. So you can run TRWS, and what you get is 1 window per image, which is most likely to be on the object, according to our model. Which basically the model, what does it say, is pick recurring objects which look similar and are at the same position with a human, but you don't know which position that. Then what you can do is start to look at it. How good does this localization work? How good a spatial model can you get out of it? And for this, we rely on this sports data set that Gupta and Davis put together in 2009. It's very popular. Lots of works appeared that use it for various goals, not only for action recognition. There are 6 action classes with 30 images per class and 20 tests.
That is why there is cricket in it.
I'm sorry?
That is why there is cricket in it.
That is why?
They have included cricket because the first author is Abhinav Gupta, he's an Indian.
Oh, I see. I see. Sure. But I like there is tennis because there is some Roger Federer images in there, and of course that makes it very appealing to us USA. See, it's an international data set. So again, the 2 state-of-the-art works on this data set. This is the famous award-winning Yao and Fei Fei 2010. The 2 highest scoring works are actually using full supervision. Again, human silhouettes and object bounding boxes in every training image. We try here to do it only from image labels. And here one can look qualitatively on some of them, then we're going to have a quantitative analysis as well. So as I said, minimizing our energy corresponds to localizing objects. And here you can see some qualitative results on the sports dataset of Gupta. And you can see that it's not always very accurate. I picked this on purpose. Sometimes it's half on the racket, you see. It's not necessarily pixel-wise, but it's typically roughly on it. And the important point is that the relative location of the action object with respect to the human is all roughly Gaussianly around at the same spot, which is what drives the whole learning algorithm. And here is a heat map visualization. I find this the best way to look at these results. So what you can do is, of course, stop pretending you do not have annotation, because you do have it on this data set. Use it to learn a KDE estimate, or a kernel density estimate, of the actual spatial relation. So if you use Grand Trove Windows, and you ask, what is the relative XY position? If the dashed white line is the human, aligned in every image, we align them by the human, where is the center of the object with respect to the human? And this is the answer, these first 3 columns, according to the ground truth annotation. And this is the answer we learn completely only by having image labels, without any location notation. So you can see that it did figure out that trumpets are played either left or left around the mouth, whereas the cricket bat is rather low there under the body. And this is an example with relative scale. This is just saying that the volleyball ball is typically smaller than the person playing it. Great. Good for the volleyball player. Of course, if you want to get good results on a test data set these days, it's not enough to just have your new component. You also need to have a lot of other features around it. So this is probably the most boring slide, but let's quickly go through it. The human object relative position is the true contribution of this work. That's what we learned the way I just told you. Then we add features like the whole scene descriptor based on GIST. We have the appearance of the object itself, which we also learn automatically with background force on surf. And then we also have a descriptor on pseudo-pose descriptor, which is basically a hog descriptor on the person. So it gives you some feeling for where its body parts are. And if you do all this, you can then ask the question, how well can the model recognize actions on a test set? Where recognize means give us semantic labels out of 6 possible actions on images in the test set. And here we can see if you only use the whole scene classifier, so you take a GIST descriptor on the entire image, you already can do something on this data because the images are so centered, and there is a lot in the just locations of the gradients that tell you about the action. And you get to about 67%. However, if you start to add elements of our approach, you add the object appearance classifier and something about the pose of the person, you can get to 76. But what is most important, in my opinion, is this jump, which means if you really add an explicit model of the spatial relation of the object with respect to the human, you get a significant improvement up to 81%. And this is particularly interesting because the spatial relation between the human and the object seems to be really informative for the action class, but we had to learn it without location annotation. And coming to the title of my talk, the 2 state-of-the-art results here, they are exactly -2 or +2% around our result. So it's quite satisfying because to get there, these guys had to train from silhouettes and stickmen and object locations, whereas these days we can get in a similar range, just quickly supervised. And here is also an interesting result, without going through every number. We entered the PASCAL Action 2011 challenge. It's always a good thing to do because there is no possibility to tweak your approach to the test set because you don't have it in these competitions. And there are a lot of numbers there. Stanford is the winner method of the challenge, and our method is the one I just explained as is, just run on the data set. And what is particularly fun is that we obtain the highest MAP overall. Basically, this measure is average precision, which is a retrieval measure as opposed to a classification measure, but it's not so important. 100 would be best. And we are basically in the range of Stanford, a little higher. But we only won 3 classes, whereas Stanford won 6. And in this challenge, it's all about getting the top rank in as many classes as you can. So it's also quite fun how stable it is over many categories. All right, are there questions on this part? Yes?
So you use basically a fully connected pairwise model for making sure that the relationships are consistent with each other, right? So, an alternative would be to have a global variable which sort of encodes the relationship, and then just have one pairwise relationship between those images and this global latent variable, right? And this would be, if you think about it in the energy minimization term, when you minimize over this latent variable, it would be acting as a higher order potential over all these things. It would be the inference would in fact be much simpler and much faster, because now you have much less edges. Earlier it was NC2, n combination 2 edges. Now you have just n edges, right?
Mm-hmm.
So having that latent variable and representing all the possible sort of relationships that could be there would be an interesting thing to do, but I think it is worth looking at because it might speed up inference.
Yes, that's a very good comment. In fact, I started to think about that possibility only after we actually get the paper through PAMI. There are some trade-offs that are interesting to look at.
Yeah.
If the space of possible, because at that point that meta node is no longer defined on candidate
Exactly.
windows, it's defined on the space of geometry.
Absolutely.
So if the possible geometries are reasonably small, let's say maybe 10,000 or so, something like that, then probably it is even faster to do what you say.
Yeah.
And it could probably even get to global inference, could be exact. That would be fun. The downside, so that's plus side, the downside is that every training image has to be similar to a single peak geometry mode. Whereas in our situation, you can have even multimodal aspects. You could have half the images form a cluster, like with the trumpet, they are to the left and the other half to the right is still fine. However, even this comment can be criticized because it all depends in the model that sits in the latent node.
Yes,
there could be a multimodal model there. It could be anything. Maybe maybe a Gaussian mixture. I don't know.
Or it could be, like, for example, rotationally invariant.
It could be rotationally invariant. You could even control it better than you control it now. You can put in the invariance there. So that would be interesting. Actually, really, I can only theorize on it. We didn't try that.
Yeah.
Okay, well, good.
One quick question. I didn't fully understand. I mean, again, with the learning, I mean, you get a single image in and you can run your method, right? But you can also run it on multiple images, right? So just actually thinking, because we had this stuff with like co-segmentation where you say discover the joint objects in the images, right? I mean, this is kind of a domain-specific co-segmentation, right?
This is all done jointly, yes. It's not one image coming in. They're all at the same time.
Yeah, but you still have train and test images, right?
Yes.
So you do all the test images jointly?
No. Once you get the model, you process the test images individually, because that's the protocol of the test set. But what I'm interested in is the training result.
Yes, but right. And the test images potentially used jointly?
Why not use the test image jointly? Normally this is called the imputation setup or so in machine learning. In our experiments in other domains than this one, indeed it brought some advantage. But it doesn't bring as much of an advantage because learning already happened. It already has a good idea of the model.
Yeah.
But in fact, ideally, there is no training or testing. There is a single gigantic problem. The big difference is that at test time, you don't even know the semantic label of the whole image. You don't even know if there is somebody playing cricket. So that's the difference. But the difference, I hope, in the future will fade. And it will all be one big inference problem. OK, now we get to something that should be closer to the interest of this group, especially to Jamie, I hope. Semantic segmentation. So you get a test image. Learning will be still soon. And the objective is to label every single pixel with a semantic class out of a small known set, say 20 or 100 classes, such as trees, cars, roads, boat, sheep, dog. And there are really many works since Jamie's CVO6 that appeared. Here are just some. And most of them, it's fair to say, they train with full supervision, which means for every pixel you have the semantic label at training time. Then at test time you have a single image and you try to label it without that input. Here we try to do it, of course, weakly supervised. So we have the training images in this form. We know which of the semantic classes appear in each image. We have a list. And we want to learn some model that you can then use to do semantic segmentation on the test set. And analog to the work I showed you before, we are going to try to solve this by automatically labeling the training set itself. So that's a common trend. If you want to be able to do localization at test time, you better be able to do it at least on your own training images first. So the way we are going to do this is with what we call a multi-image model. Basically, we encode the entire training set. So that's a key idea. The entire training set gets encoded into a single graphical model where the nodes express superpixel appearance and superpixel latent variables that encode the label, the semantic labels of the superpixels. So basically, we decompose the training images into superpixels, like here. Every superpixel is assumed to belong to exactly one semantic class. This has been studied a lot before us. We believe that that works. And this we do to reduce the total complexity of inference. So now, let's go through our model. So the white nodes you see are latent superpixel labels. That's what we really are after. We would like to recover the label, say this superpixel is dog, the other is grass, the third is road. That's what we really wanted. They are latent at training time. Then we observe superpixel features. We will see later which features we use. Typically, text and forest type of things are good. Then we are going to observe another thing, which are image labels. So at the level of the entire image, we do know with semantic clustering there. So an image label could be AC, let's say airplane and cat. DFG would be dog, fountain, and grass. So one of these plates I show would be the entire data we have for a training image, all the variables in there. The edges represent potentials. So the first unary potential, pi, says that a superpixel can only take a label that has been given to the image. Basically gives infinite energy if the superpixel tries to take some other label. And gives 0 if it's one of the allowed labels. Then we're going to have a classic likelihood unary potential. If you have the appearance model of a class, let's say you know the distribution of grass in your text and forest space or in anything, any other appearance model, then you can use the unary potential to evaluate the probability that that superpixel will have a certain label. Of course, we do not have these appearance models at the beginning. We are going to see how we solve for that. Then we have classic pairwise potentials that are sitting within a single image. So this is a classic contrast-sensitive smoothing that is popular since many years. The more interesting part is the pairwise potentials between images. This is the really interesting part of this work. So we are now going to have edges that connect superpixels between different images. And only between different images that share a semantic label. So you do set intersection of the two sets of semantic labels. If there is one in common, then you're going to try to connect. We'll see how we do that in detail in the next few slides. But the interesting point is that similar superpixels in two different images that share a label, they are encouraged by this potential to take on the same label, although you don't know which one. If they're both green and they sit in images with grass and dog, they could take grass or dog, but please not something else. That's what the potential says. And here you can see the math form. This is just the appearance and the similarity measure, let's say chi-square between self-descriptors or the difference in the leaf distribution of a text and forest. Notice how the potential is so modular because it gives 0 energy as soon as you take the same label and above 0 for any different label. The penalty that this potential gives vanishes to 0 as the similarity between the superpixels gets too small. So two very appearance dissimilar superpixels can take any label they want. So this modular aspect is important in our inference procedure.
So
yes.
So I think this is a very good model. I had missed it, but very nice. The one issue that might happen, and this is sort of the one that we faced in the ECCV 2010 paper on coaccurrence, was that the y2 variable is observed, right? It says
which variable?
The y variable.
Y?
The y variable.
Yeah, the y variable. In our case, it's not observed.
Yeah. So the y variables are the ones which say which labels are present.
Yes, the capital Y. Yes.
Yes, the capital Y.
Good. Yes.
Right. So they are saying, for example, y2 is saying A and B should be present in this image, right? And the latent variables say I can only take A or B.
Right.
But the energy does not impose the constraint that at least one pixel or superpixel has to take the A or B label, which is the most difficult constraint in the...
It is a very nasty constraint because, of course, it's a cropped, highly nonlinear constraint. I mean, you could ask Boykov on how much he likes to ensure, start to count, he should take 5 different. I don't have a mathematical answer to that in my talk, so I don't know how to enforce that. But I have an answer through objectness, on how that happens naturally in our model.
Yeah, but the
It's
point
going to
is,
come in 3 slides.
yeah, but so the reason why I was bringing this up, because this was a constraint that came in the ECCV 2010 paper on object co-occurrence, right? If you have certain subsets of labels that you really want to enforce, if you want to say grass and cow should definitely co-occur. If there is cow, then I definitely need to see grass.
Right.
So that was a part of our ECC paper, how to implement these co-occurrences. And there exactly this sort of constraint comes in. And we gave an inference algorithm to sort of see where these sort of constraints you need to impose and where you don't really need to impose.
Sure. So this is an interesting complementary aspect.
Yeah.
If we could be able to, enforce, let's say, using all the labels or even which labels, that could be added on top.
Exactly.
Here, what we're trying to do is to, let's say, regularize in a certain sense the latent learning, the problem of learning the whys, and through these connections between the images that make it, again, it's all about making the space of possible answers smaller.
Yeah.
And having that, I see it as a complementary module we could try to add.
Yeah.
So now, the interesting question is, okay, cool idea, we try to connect different superpixels to transmit, propagate the label information better. But which superpixels? Now, there are really too many to connect them all. So first of all, only 2 images that share a label. Okay, good. That's not even an approximation, that's just the right thing to do. But then we have to start to approximate. So and how do we approximate? Well, we know that if 2 superpixels are very dissimilar, okay, then this potential becomes less and less present. Because as the similarity goes up, it gives 0 all the time. Right? So the potential fades out as the superpixel dissimilarity grows. So we better, if we have a budget, we can only pay n connections, we better spend them on highly similar superpixels. And that's something you can measure without looking at the labels. That's very important, because you need to build the model before you recover the labels. So in the moment we build the model is data-driven. The connections are not hardwired at the beginning. The algorithm chooses where to put the edges. And you can give him a budget. Typically, for every single superpixel, you connect it to k. That's a parameter you have to give him. Nearest superpixels in images that share the label. So the most similar ones. Then if you want, you can refine it. You can say, don't take more than p superpixels in an image so that it doesn't all go in the same patch of grass. It diversifies more. You try to connect you try to build a sparse model, but variably connected. The best is to connect a bit of everything with everything else to propagate the labels best. So here is an example with this superpixel would have been connected here in this image, here in this image. See, here there is no grass. So maybe this brown patch is not so useful, but this image shares a label. It has road. Of course, the computer doesn't know now that this is not quite a road. It's more like a patch of grass, but it still connects it to the closest thing you can find. And sometimes it goes on grass, sometimes it goes on something else. But most important, we preserve these connections that will be driving the learning aspect. So this was the definition of the model. Now, let's talk about how we solve it. We want to solve for y and theta. Y is the latent superpixel labeling, and theta are the appearance model parameters. So basically, these appearance model parameters are basically machines. You give them a superpixel descriptor, and it tells you a probability distribution over the labels. It tells you this is more grass, a little bit less cow. And there you could use anything, basically. But we'll see what we use. So if we freeze theta, then we can say, if somebody gives me the appearance model parameters, I can reproduce the superpixel labeling y by running inference on this model. Basically, our model, all the potentials are submodular between every pair of labels. Therefore, we can run alpha expansion on it pretty nicely, and it gives us a good approximation. Now, in practice, this situation here is more a situation of inference test time. At training time, we neither have the superpixel labels nor the appearance model, so we gotta find both. How do we do that? Well, that's nasty, because the appearance models are typically continuous, and the superpixel labels are discrete, and they are connected in highly nonlinear fashion. So to find a global solution, we at least weren't able, and we don't think it's possible today. However, we can resort to a traditional iterative minimization. We can start from an initialization. In our case, initialization is very simple. We set the superpixel labels randomly, as long as they fulfill the image label constraints. And then, given fixed image labels, superpixel labels, we can train the appearance models in a standard supervised learning fashion. At this point, you fall back into supervised learning once you have the superpixel labels. Once you have then trained the appearance models theta, you can use them, fix them, and use alpha expansion to update the superpixel labels. And you can do the 2 in iteration, and actually, you can actually prove that the total energy goes down at every iteration if you choose your appearance model properly.
Just a comment, I mean, you're aware that it's the same as what we've done in GrabCAD?
Of course.
And that's, that we had an ICCD 09 paper where we do it globally optimal.
Yes, with Vicente.
Okay.
In the case, the appearance models are color histograms. In your
Yeah, we
paper.
do that, yeah.
In the case, the corresponding are color histograms, but
Yeah,
not for arbitrary appearance
exactly,
models.
yes. But I was just one, yeah.
I am perfectly aware, and I'm
no,
perfectly sure we cite GrabCAD in our work.
Yeah, no, but also that it's like potential, there might be other optimization techniques with such.
Sure. So iterating between updating appearance models and some other latent variables is a very common thing to do in GrabCAD and in other approaches as well. It's very important to realize that the global optimality in Vicente and Roter, it's restricted to a certain class of appearance models that we didn't want to use here. We wanted to use more complex. In this case, we used some random forest classifier. So we didn't want to restrict ourselves to what can be done globally optimally for the sake of it.
No, but it was not global optimal, right? So NP had problems still.
Yeah, but 60% of the paper.
Yeah, you get global optimal.
Well, it's very close. I mean, in that paper, you're really very close to it, like, to be fair. But it's restricted to that appearance model.
Yeah.
Okay, very good. Now we get to, basically, if you run this, you get your training done. Now we get to the test stage. So at test time, one thing you could do is to just take your appearance models, your theta, and use them in your test image, with a pairwise potential that enforces smoothing, and cross your fingers and pray hope for the best, and something will come out. And something good comes out. However, you can do better. You can do better, inspired, for example, by Shotton and not just a CAPR8, but also other works, and pull on the idea that globally similar images often have a similar distribution of semantic labels. It's important to realize what global similarity versus local similarity is. Instead of looking just at one superpixel, you can look at the entire image, say with GIST distribution or for dense surf distributions, and compare the entire image. This is something that Alyosha Efros and Antonio Torralba like a lot to do. And you can actually seamlessly encode that idea and create more local random field models. And how does it go? Well, analog, I would say, like Shotton et al. CPR08, you can take the test image, have a global descriptor, retrieve the most similar training images. They have image level labels. So now you can do a histogramming of these image level labels. You get a probability multinomial distribution if you want, P, which you can then use as a unary potential. Instead of the hardwired infinite or zero constraint we had at training, at testing we have a more smooth preference potential mu that replaces the ground truth labels. So instead of the ground truth labels, now we have this image level prior transfer from the training. And now you can integrate the test image. You can plug it inside your multi-image model. What you see around here, these gray nodes, these are the training images that are similar to it. Now they are all gray because at training time we fixed the superpixel labels, and the pairwise potential between them disappear because they don't make any sense at this point. And they're just fixed. Now you can plug in your test image and connect it with pairwise potential to the training superpixels, analog to what we did at training time, right? So in this fashion, you get this nearest neighbor label transfer effect, and at the same time you get the pre-digested appearance model effect as well. And the two together, they're really helpful. So basically, you can unite a little bit these two schools on how to label test data, the nearest neighbor transfer school and the I pre-digest appearance model school, into a single model this fashion. And notice that this is identical to the training model, essentially. All the potentials are the same, all the connections are the same. Just the test image is special because she has a special unary potential which is soft in the label preference instead of being hard. And of course, you can run alpha expansion on this as well. Now, the unary potential, I kept postponing them because that's my favorite slide, that's why. We already revealed that we have some text on forest as appearance model, but we have also an objectness unary potential. That's cool. As I said, this is a magic recipe that works in many works. You can take your sampled objectness windows, and turn them into a per pixel unary potential. You can say, if you sit on a pixel, you can see how many objectness windows passed through that pixel. You can normalize this over the entire training set and turn it into a probability 0,1 per pixel. Now you can use that to be a unary potential for the superpixel. And why is that good? Because you can split the semantic classes into two disjoint sets, the set of things and the set of stuff. And basically, in this example you see, if you don't know what the label of this duck is, you don't know it. But the random field will tend not to give it a grass or sky or road label. It will prefer to give it duck, dog, or building, or something foreground label. And basically what happens is that this prevents a very nasty phenomenon that has been observed in many papers on semantic segmentation, which is background flooding. Typically, if you have a little bird in the sky, the pairwise potentials, they hate to delineate small, long contours around a small region, and you tend to swallow it. It becomes just sky. The bird is gone. Whereas with this potential, you can smoothly prevent that. You can have the bird become not sky. It could become a dog. It doesn't have to become a bird, but it cannot stay sky. This objectness potential prevents it. And of course, as soon as you start inserting soft preventions this way, the image labels come in, and you know there is no dog in the image, and it becomes bird. And all of a sudden, you solved really, I would say, a big problem in the weakly supervised aspect to find small objects against large background areas. And here's some results to conclude. We have results on MSCC21, the probably most popular dataset for semantic segmentation. It is fun and very much experimented on, but it's rather small and, in a way, easy. Therefore, we also experiment on the recent SIFT-flow subset of label me, which has 5 times more images and is a lot harder. There are a lot of little windows and little fire hydrants in there. It's really tough stuff. We use the standard training test fits in the literature. That's not as interesting. What is my favorite result is not even the test time, as I was trying to pitch to Karsten before, but I like most the results at training time. So how well do we recover the localization information in the training images? Here are some examples of it and quantitative evaluation about to come in the next slide. We can see that if you have of course, all the images are treated at the same time, but that's an output per image. You can see how you can find little cars among vegetation and road, and even walls of bicycles. So basically, this is the input to the algorithm times 500 images, and this will be the output of your learning algorithm. And if you look at per class average pixel label accuracy, so I don't know how used you are to these measures, but basically, there is a measure that is, what is the average per pixel labeling accuracy, and I don't like that at all, because if you start to score on sky, road, and grass, you're already high, and you forgot about the objects. And then there is another measure which I believe is more relevant, which is per class average pixel labeling. So you do average per class, and you average over the classes. So classes that occupy a small image region, they count as much as sky. And that's all the results I report on. Here is a table that shows you, in training and in testing, the per class average pixel labeling, if we take our model with multi-image connections switched off or on, and the objectness potential switched off or on. Because these are the true, really new points of the work. So we wanted to see that we do well because of that and not because of some engineering reason. And it's fun to see that both components help. So if you go from off to on for objectness, you get a massive 26% training set labeling improvement. And for MIM, you get also a nice 15%. And if you combine the two, you get beyond each of the two. 3% here and 14% in this direction. So objectness really, really help. Even after the multi-image model, still gives you another 14%. Yes?
Just one question. The objectness in this case, it's the general objectness thing you have trained on PASCAL or some other data set? So has there been some extra supervision flowing into the objectness?
That's a very, very good question and very unfair for me to not to have mentioned. Yes, very important. The objectness measure needs supervision. But however, we trained it from images that are unrelated to neither to PASCAL nor to this data set. Of course, there has to be some grass in those images somewhere, but we didn't label it grass. It's trained on 50 separate images that come mostly from the Gavrila pedestrian, India pedestrian, and data sets that are not involved here. And the supervision is only 50. They contain 300 objects. The supervision at the level of a bounding box on each object. The full detail of this weird training set are on our website. We chose that training set so it doesn't overlap with anything that people work on today. So they can reuse it if they download our code without trouble. Good point. So at test time, it's interesting how the synergy between the two is. So of course, objectness basically gives you 6% and mean 2, but together they give you another 7% on top of their own. And the synergy is interesting. Basically, the synergy effect is bigger than the individual contribution. And I believe this happens because at some point, once you put objectness in, you disambiguate certain situations like dogs on grass that then propagate through the multi-image potentials to many other training images. And then a comparison to, well, here is some illustration results on the test set. This is to show that even after you have trained, this is basically the test image. This is the ground truth, the little thingy. These are the unary potential after training. So they have been trained weakly supervised, but now they are run on the test image. And you can see that they don't solve the whole problem on their own, even though they've been trained as cleverly as we managed. Here you can see how mixed the segmentation is for this. So the pairwise potentials within the image and between, they still help really a lot. And then the question is, how well do you do over the entire state of the art, especially how well do you do compared to fully supervised methods, because your title of your talk, is kind of promising. And the answer is we don't do as well as the most recent state of the art, but we do as well as state of the art of 2 years ago, let's say, for fully supervised. This is quite amazing, I think, given that this is completely weakly supervised. So the earliest weakly supervised work we know on MSRC does about 50% on the test set. Our student last year had a worse performing work that still got published. So it's very nice the community is ready for ideas and results. And this is the work I've shown you today, which does 67% on the MSRC test set, training weakly supervised, which is identical, very interestingly, to Jamie's VPR08 fully supervised, a bit better than the original 58, but also below, to be fair, the most recent Ladikis works that go another about 10% above. On the harder, a lot harder label me, so it's interesting to see the results. The fully supervised work that basically started it as the award-winning CPR09 by Liu and Toralba was at 24. They also ran Shotton's ECCV06 version on that code themselves. They got around 13. Now we are at 14, so we are in line at least with one fully supervised, but again below the state of the art by a margin there. But what is fun is that the gap is closing, I argue. At least we start now to be with a weakly supervised semantic segmentation in the range to, let's say, 2-3 years old fully supervised methods, which for me is a very interesting result and shows that the weakly supervised community is catching on. Maybe one day we really will be able to get rid of all mechanical Turk and do it automatically. So there's a lot of people that work on these projects. Thank you.
Very good. Thank you very much for an amazing talk. Lots of questions. We're going through them already. Perhaps we can take one more. Come on. Don't be shy. Push me. I'm sure you have one more. Oh, Carson. There we go.
Have you ever seen, I've seen recent work like on supervised, which tried to do pixel accurate labeling, and they had, they actually argued that the results were worse than doing not exactly relying on it. So there might be mistakes by the user, right?
Mm-hmm.
If there are mistakes by the user, it might be actually with a slightly weakly unsupervised or doing a band around it might be actually better. Have you ever seen that actually better?
Wow, that's a great question. On the MSRC, I've seen it in the sense that the ground truth annotation of MSRC is quite rough.
My fault.
It's quite rough. Actually, there is a good 5% Fairback computer.
I'm actually surprised you're using it.
Fairback is, well, we're running our results to the 1% and thinking maybe we should run it to the 5% so that it's at the accuracy of the ground truth data. Seriously, Fairback was computing about 5% of pixels are missing or something. But actually, if you look at the output, we only saw that certain tiny bits of animal parts were better. So sometimes you have dogs and we get the paws, right? Whereas the annotation is like a circle or something.
Yeah, yeah.
So that we do notice. But on average, no, the ground truth on average is better.
Yeah, yeah.
Often, sometimes our method misses an entire build. So.
Sure.
But in terms of contour level, if you get it right, the exact contours are about better than the ground truth.
Yeah. That's what. That's
when it gets right, it gets better than ground truth, but most of the time it doesn't get it as right.
Great, thank you very much, and we thank the speaker again.